Hey everyone, we're going to be continuing our derivative rules here with the last two rules. So now we're going to be able to apply more complex derivative rules to quotients and products of functions and take high order derivatives of functions. So let's see what kind of vocab we're going to be dealing with. Limits, we can't get away from them. Derivative, of course. Differentiability, product, quotient. Product, remember, is two things multiplied together. Quotient is two things divided. Prime, so remember we deal with f prime, and high order derivatives. So we're going to see some second derivatives, third derivatives, that kind of stuff in this video. Let's take a look. So let's review the ones we have so far. In our last video, we talked about the derivative of a constant is always 0. The power rule, which we saw was really useful for like x to the fourth, gives you like 4x cubed. Derivative of a constant times a function, you can pull the constant out, take the derivative of the function, and then multiply it afterwards. You can add or subtract derivatives individually, which is pretty nice. So notice we did not have a multiplication before. So adding and subtracting functions is really easy with derivatives, but if you want to do the derivative of the product of a function, it is not equal to the product of the derivatives. This is really important. So if you're doing the derivative of f times g, it is not the derivative of f times the derivative of g. That's an important one. You have to do this, and I'm going to do this proof in a separate video because the proof is not something you need to know, but I think it's kind of cool to see how it's proved from limits. So what they're telling us here is if you want to find the derivative of f and g, f times g, you leave the f function alone, multiply by the derivative of g, then you add to it, you leave the g alone, and you multiply by the derivative of f. So let's try a simple one. I'll do one that you could do by actually combining functions, but we'll just show that it's the same thing. So if you want to do the derivative of, let's say, like x squared times x cubed. Now, of course, there's some out there that are saying, well, that's just x to the fifth. Couldn't we just combine them? Yes, but I'm going to show you that this works. Okay, and I'm actually going to show you that it doesn't work if you do the derivatives separately and multiply them. So let's show that first. If you do the derivative of x squared, that's 2x. Derivative of x cubed, that's 3x squared. Multiply them together, you get 6x to the third. But look at this. This is x to the fifth, right? Derivative should be 5x to the fourth. Those are not the same. So this doesn't work. So let's try it with the formula that we have here and see if it works. So we leave f alone. So this is f, let's say. So we leave that alone. Multiply by the derivative of g, which is 3x squared. Then we add to it. This time we're going to leave the second one alone. So we have x cubed multiplied by the derivative of the first, which is 2x squared. So if we combine here, that gives us 3x to the fourth plus 2x to the, this should be just x. Sorry about that. 2x to the fourth altogether gives us 5x to the fourth, which is indeed the derivative of x to the fifth. So we just did one example, but this works for any product of functions, which is kind of cool. I tutored a student in Florida who had a way of remembering this. She said, oh, our teacher taught us that. It's called foggy goffy. And I was like, what the heck are you talking about? Because when she said foggy goffy, I always thought this. Foggy goffy. I was like, what the heck is that? And she said, no. It's like this. Foggy goffy. Foggy goffy. And the reason she told me it's like because it's f times g prime, g times f prime. Foggy, F-O-G-I, Goffy, G-O-F-I. So if that's useful to you, cool. I just remember you always leave one of them alone and do the derivative of the other, then you add it in the opposite direction. So I left the x squared alone, took the derivative of x cubed, and then just leave the x cubed alone and add the derivative of x squared. All right, let's check out the quotient rule. Quotient rule is one of my favorite rules in calculus because it has a cool little rhyme that goes with it. So let's see how it's similar to the product rule. So on the top here, we have the g of x, we leave it alone, multiply by the derivative of f. Then we subtract, leave the f alone, multiply by the derivative of the g. Then on the bottom, we have g of x squared. Notice there's no derivative on the bottom, it's just g of x squared. So let's try a simple example. We'll kind of do it like we did last time. So let's do, how about x to the fifth over x cubed? Now we know that that's x squared, right? So our derivative should be 2x. And let's use the quotient rule and see if it works out. So do the bottom function, leave it alone. multiply by the derivative of the top, which is 5x to the fourth. Subtract top function, we leave it alone, times the derivative of the bottom, which is 3x squared, and divided by the bottom one squared. So x cubed squared. No derivatives, just square the bottom one. So let's put it together here. That's 5x to the seventh minus 3x to the seventh divided by x to the sixth, which is 2x to the sixth, seventh, divided by x to the sixth, which is indeed 2x. So it works out. So there's a way to remember this one too, kind of like the foggy Goffey, except this one is much more widely known. Your book says something ridiculous for this. I'll tell you what it says in a second, but the way that I say it is, and this is worth writing down, seriously, write this down, low d high minus high d low over the square of low we go. So I would encourage you to say this as often as you can because it will make you never forget it. Low d high minus high d low over the square of low we go. Say it with me. Low d high minus high d low over the square of low we go. One more time. It's like the bouncing ball in the Disney movies. Low d high minus high d low over the square of low we go. So the reason this helps me is because d stands for derivative, right? So low you leave alone. D high, you take the derivative of the top function, minus high d low over the square of low we go. You can even see it here. Low we leave alone, d high minus high d low over the square of low we go. Kind of cool. Let's try it with some examples. So let's try the product rule first. So we've got the product of two functions. We could FOIL this out, but we're going to use product rule to do this. So foggy Goffey, if you will. I'm going to leave the first function alone, so f prime of x. Leave the first one alone, x squared plus 1. Multiply by the derivative of the second, that's 3x squared. Plus, now we're going to leave the second one alone, x cubed plus 3, and multiply by the derivative of the first, which is 2x. Now remember, you don't have to do algebra. Stop right there. We're done. That's the derivative. Next one, why don't you try this with low d high minus high d low over the square of low we go. Go ahead and pause the video, see what you get. All right, let's try it together. So it's going to be low d high, which is 2x, minus high d low, 2x, over the square of low we go. X squared plus 1 squared. I would stop right there. Why go further if you don't have to, right? You could square this out. You could distribute some stuff up here, but man, that negative sign, that looks ugly. I don't want to deal with that. Just stop right there. All right, higher order derivatives. So this is something we haven't seen yet. We've seen f with 1 prime. What do you think it means if we have 2 primes? This means the second derivative. Second derivative. Okay, so let's see what happens. So f prime of x is 3x squared minus 5, right? 2 is nothing, so it's just 0. What do you think f double prime is? It's 6x. You just do the derivative again. That's all there is to it. So what do you think this is? This is just Leibniz notation for the third derivative. So let's do it. So d dx of f of x is going to be negative 8x to the third minus 6x plus 1. D squared dx squared f of x is going to be negative 24x squared minus 6. And d cubed y dx cubed is going to be negative 48x, and the constant goes away. Notice that if it's a polynomial, terms keep kind of dropping off. Eventually, every polynomial would turn into 0 if you take enough derivatives. Now, some people always say it bothers them that the cube is here and here. Basically, what's happening is you're doing d dx of the function. So what happens is you end up compiling d's up here, so it's d squared, and then on the bottom you have 2 dx's, so it's dx squared like that. And the more you get, you just keep increasing that number. That's all there is to it. That's it for higher order derivatives. That's it for this video. I will see you for the proof video if you want to see the proof of the power rule and of the product rule. I'll see you there.